All right, so let's look at an example. Find a negation of for each x squared is bigger than x. So what is that going to be? Negation of for each x squared bigger than x is same as there exists x, right? Again, look at the first identity. Negation for each x p of x is there exists x with negation p of x. P of x is here x squared bigger than x. What is negation of x squared bigger than x? If x squared is not bigger than x, it means x squared has to be less than equal to x. Okay, that's it. So another example, show that a negation of there for each x, p of x implies q of x, and there exists x with p of x conjunction negation q of x are logically equivalent. Okay, so we have two compound, again, propositions and predicate basically because they depend on x, and we want to show that they are logically equivalent. So this is basically we want to prove an identity, right? So how do we prove identities? Even in pre-calculus, let's say you want to prove a trigonometric identity, for example. The way you could do it, you could start with the left-hand side, for example, and then do some type of simplification or calculation, manipulations, and get to the right-hand side at the end. So we can do the same thing. We can start, for example, left-hand side, which is negation for each x. P of x implies q of x. So we can start with this and try to get to right hand side. So negation of for each x something. So we can use this identity one here. Negation of for each x p of x is there exists x with negation p of x. So I can say that this one by one above is there exists x with negation of p of x implies q of x. So up to here, it was very straightforward, right? Now, I have negation of p of x implies q of x. And what do I need at the end? Because look at what we are supposed to get at the end. At the end, I have to get this guy here. There exists x with p of x conjunction negation q of x. Well, so far I got this, there exists x, so this part is already done. Now this part I'm showing with the cursor, this part I have to show that it's same or equivalent with this part. How can I do that? So there is an implication here, but there is a conjunction here. So how can I relate implication with conjunction? Well, I have to think about the identities that we have learned before. There was an identity that relates implication with, well, not conjunction, but disjunction, but then we'll see that at the end conjunction will appear. But at least I want to get rid of implication and replace it with either conjunction or disjunction, and then I'll try to figure out the rest later. Do you remember what identity did we have today that relates implication with disjunction? So let's go back. Here, P implies Q is equivalent with negation P, disjunction Q. I want to use this identity. So it's identity 8 in my page 4. So I can say that this one by 8 in page 4. I can say that this is same as there exists X with negation P of X or Q of X. And then this is equivalent with there exists X with, now negation of, let's say R disjunction S. What is it? By De Morgan's law is negation R conjunction negation S. So this is same as saying that negation, my R is negation P here. So negation P of X. Disjunction becomes conjunction, and then negation Q of X. And then this is same as saying there exists X. Negation P of X is P of X. Conjunction negation Q of X. Which is what I needed, right? At the end here. There exists X P of X conjunction negation Q of X. Which is exactly what I got here. So this is like proving again, like I said, identities. You start with the left-hand side, do some simplification, and when we get, then we get to the right-hand side. All right, and then we will move on to the next section, 1.5, 1.5 nested quantifiers. So we want to know about the, we want to understand and find out about the truth values of statements that contains more than one quantifier. So the goal here is to understand statements with more than one quantifier. Now, the first case that we want to look at is a statement of the form, let's say for each X, for each Y, P of X and Y. So please remember that we want to look at the cases where we have more than one quantifier. So right now we have two quantifiers, both universal quantifiers, one on X, one on another variable Y. And then we have a statement of the form P of X and Y, which can be true or false for each pair of X and Y. Okay, so let me give you an example first. We want to know under which circumstances we can say this statement is true and when can we say it's false. So let's look at an example. Let's say if I say for each class in Columbia College, and each student in these classes their GPA is more than 3.6. So when can we say that this statement is true and when can we say it's false? So this is statement. So this statement will be true if, so we want each class, each student in each class to have GPA more than 3.6. So it will be true if each student in each class has GPA more than 3.6. Basically, every student in Columbia College must have GPA more than 3.6. Every student because each student in Columbia College will be in some class, right? At least one class. So every student in every class must have GPA more than 3.6. And when can we say it's false? So this is statement will be false if there exists at least one student in one class at least one class whose GPA is less than or equal to 3.6. If there exists at least one student with GPA less than 3.6 in at least one class, then this statement will be false. But if every student in every class has GPA more than 3.6, this statement will be true. So I can say that so the generalization basically will be, we can say that, we say for each x, for each y, P of x and y is true if P of x and y is true for every pair of x and y. And it will be false if P of x and y is false for at least one pair x and y. So let's look at a mathematical example as well. So let's say for each x, for each y, x plus y is equal to y plus x. So this one is true, right? Because for every pair x and y, we have x plus y equals y plus x. Now another example, let's say for each x, for each y, x plus y equals 0. So previous example, any pair of x and y that you imagine, x plus y is equal to y plus x. For example, 2 plus 3 is same as 3 plus 2. 5 plus 9 is same as 9 plus 5, and so on. Any pair x and y that you consider. But what about this one? Can I say that for any pair x and y, x plus y is equal to 0? The answer is obviously no, right? So there are so many different pairs of x and y, where x plus y is not 0. For example, 2 plus 5 is 7, which is not 0. So this one is false. Since, for example, 2 plus 5, it is not equal to 0. So remember, we said that this statement for each x, for each y is false. It will be false if p of x and y is false for at least one pair x and y. Well, right now I just found one pair, which is namely 2 and 5, for which 2 plus 5 is not equal to 0. And that's enough to show that this statement is false. Okay, so this was the first type of nested. Remember, our goal is to study nested quantifiers where we have a statement with more than one quantifier. So that's the first one we want to look at. Now the second one, let's say there exists x, there exists y, p of x and y. So when can we say that this is true? When can we say this is false? So this statement is true if p of x and y is true for at least one pair x and y, and it will be false if p of x and y is false for every pair x and y. Okay, so it's kind of opposite of the previous case. In the previous case, in order to show it's true, it has p of x and y should be true for every pair x and y. And to show it's false, it has to be false for at least one pair x and y. Now this is the opposite. It will be true if for at least one pair it's true. It will be false if for every pair x and y it's false. You can think about the example that we said again. Classes in Columbia College and students in those classes. When can I say that? If I say, for example, there exists a class in Columbia College for which there exists a student in that class that has GPA more than 3.6. When can I say it's true? When can I say it's false? Well, it will be true if at least one student in Columbia College in at least one class has GPA more than 3.6. And it will be false if every student in every class, meaning that all students in Columbia College, has GPA less than 3.6. So let's look at an example. Let's say if I say there exists x, there exists y, such that x plus y is equal to 0. This one is true or false. So can I, as we said, it will be true if it's true for at least one pair. Well, obviously there are so many pairs for which this is true. What are they? For example, 2 plus minus 2, 1 plus minus 1. For all these pairs, x plus y is 0. So this one is true. Since, for example, 1 plus minus 1 is 0. Or another example, let's say there exists x, there exists y, that, for example, x plus y is equal to 5x minus 2y. So this one is also true. Well, and again, if we want to show it's true, we need to find at least one pair for which this is true. So how can I find at least one pair? Well, we can do some simple calculations. So this one, if I simplify, x plus y, 5x minus 2y, this is same as saying that if I take x to the right hand side, it becomes 4x, to y to the left hand side becomes 3y. Right? And then, well, we just need to find an x and y where 4x is equal to 3y. So for example, thus x plus y equals 5x minus 2y holds for x equals 3 and y equals 4. I want 4x to be equal to 3y. So there are so many options for x and y, but one simple option is that I can choose x to be 3, because then 4x becomes 4 times 3, which is 12. And then the right-hand side will become 3 times 4, which is also 12. So I found one pair for which this holds. And then that means that this statement is true. Now another example, let's say there exists x, there exists y, such that, for example, x squared plus 1 is equal to minus y squared minus 2. So this one is false. How can I show it's false? I have to show that the statement p of x and y, in this case is x squared plus 1 equals minus y squared minus 2, does not hold for any pair x and y. Well, that's very easy to show, because any pair x and y that you imagine, you consider, x squared plus 1 will be positive, a positive number, minus y squared minus 2 will be a negative number, and the positive number can never be equal to a negative number. So it's false, since for any pair x and y, x squared plus 1 is positive and minus y squared minus 2 is negative. And that means x squared plus 1 is not equal to minus y squared minus 2. So that means this equality does not hold for every or for any pair x and y, and therefore this statement is false. All right, so the next type of nested quantifiers that we want to look at is a statement of the form, let's say, there exists x for each y, p of x and y. Again, let's think about the example of classes in Columbia College and the students in those classes. So if I say, for example, there exists a class for which every student in that class has GPA more than 3.6. There exists at least one class such that in that class, every student has GPA more than 3.6. When can I say that this statement is false? Well, just imagine. If there exists at least one class, so it should be a very good class, right? So 200 level maybe, or a class of top students, such that in that class, every student has GPA more than 3.6. So this statement will be false if, well, none of the classes is a very top class in this sense, meaning that for every class, there must exist at least one student with GPA less than 3.6. In that case, I can say this statement is false, right? So I can say that this statement is true if there exists at least one x for which p of x and y is true for every y. And this statement is false if for every x, p of x and y is false for at least one y. So let's look at an example of the mathematical example that we considered in the previous cases as well. Let's say there exists x for each y, x plus y equals 0. So can I say that there exists at least one value of x such that for that value, for every y, x plus y is 0? Well, to get to have a better understanding about this, let's think about few values of x. We want to know whether there exists x with some property, yes or no. Well, let's think about some examples to get the idea. For example, if x is 1, then I need 1 plus y to be equal to 0. So can I say that 1 plus y equals 0 is true for every y? Well, obviously no, because 1 plus y is equal to 0 only for one value of y, not for every y. Well, therefore x equals 1 cannot be the x value that we are looking for. We are looking for a value of x. If this wants to be true, at least one value of x must exist for which, for every y, we have x plus y equals 0. So x equals 1 is not that x value. What about x equals 2? Well, 2 plus y equals 0. Can we say this is true for every y? Again, obviously no. 2 plus y is equal to 0 only for one value of y, which is y equals minus 2, not for every y. And similar argument holds for other x values as well. So I can say that this is false since, now how can I show it's false? Look at the definition that I mentioned here. The statement is false if for every x, p of x and y is false for at least one y value. So since for every x, x plus y is not equal to 0 for which y value? So can you tell me which y value should I use? Let's say x is fixed. X is fixed and given. So for example, x could be 2. 2 plus y is equal to 0 for, we want 2 plus y not to be 0. Now, which y value can I use in order to have a guarantee that x plus y is not equal to 0? Now, if it's 2 plus y is not equal to 0 for many y values, for example, 1, 2, 3, 4, 5, minus 1, anything except minus 2. But in general, remember, we said that, we have to prove a statement in general. We cannot prove by giving just examples, right? We'll get into the methods of proofs later. But x plus y, we want it to be not equal. We don't know what the value of x is here. We just know that there is some x value given to us. It could be anything. And I want to find at least one y value for which x plus y is not equal to 0 for sure, right? So it's important that it has to be not equal to 0 for sure. If you choose a y value for which x plus y might be 0, might not be 0, then that's not good enough. For example, one attempt is that I could choose, for example, y equals x. That's a very simple attempt. And then x plus y becomes 2x. So can I say that 2x is not 0? Well, no, I'm not sure whether 2x is not 0. Because 2x will be 0 if x is 0, right? And I don't know whether x is 0 or not 0. I just know that x is some real number. That's all I know. It could be anything. So y equals x works, but in the case that x is not 0. If x is 0, then x plus x becomes 2x. If x is 0, 2x will be 0. I want x plus y to be not equal to 0 for sure. So which y value should I use? We can use y equals, let's say, minus x plus 1. Right? Because x plus minus x plus 1 will be 1, which is always not equal to 0. See, if I choose y to be equal to minus x plus 1, then x plus y is not equal to 0 for sure. I have a guarantee, because no matter what what the value of x is, x plus minus x plus 1 is 1, and 1 is always not 0. And remember, I was looking for at least one value of y for which x plus y is not 0. One value is enough for me. Let me show you again the definition. The statement is false if for every x, p of x and y is false for at least one y. So I said that here, that's exactly what I showed. I said, let's assume x is any given number, since for every x, x plus y is not equal to 0 for y equals minus x plus 1, which is at least, which means I already found one value for y for which x plus y is not 0, meaning that p of x and y does not hold, or it's false. So this means that this whole statement is false as well. So we showed for every x, there exists at least one y for which p of x and y is false. This means that the statement above is false. All right, so this was the third type, and the fourth type is, so this one we said there exists, so for each x, there exists y, p of x and y. So this one, let's compare it again. Let's think about it in the context of classes in Columbia College and students in those classes. Previously, we have had, there exists a class for which every student in that class must have GPA more than 3.6. Means that in the previous case, that meant that we must have a class which is a very, very strong class. all the top students must register in that class in a way that for that class, every student must have GPA more than 3.6. But what about this one? What does this say? It says for every class in Columbia College, there exists a student whose GPA is more than 3.6. So this means that, every class in the Columbia College is not necessarily very, very strong, but it's not too weak either. There exists at least one student in every class that has GPA more than 3.6. So if I want to describe briefly, previous case means that among all classes in the Columbia College, at least one class must be very, very strong. Maybe it was, for example, analysis class, which is a very tough course, and therefore every student in that class must have GPA more than 3.6. But this case, we are not requiring to have at least one very, very strong class. This case, we are saying that every class at Columbia College does not have to be very, very strong, but it should not be very weak in the sense that at least one student in that class must have GPA more than 3.6. So this one says every class is not very weak in the sense that at least one good student is in every class. Previous case was saying that at least one class must be very, very strong, meaning that every student in that class must have GPA bigger than 3.6. So you can see that depending on the context, we may require the previous case, which we call it 3, or we may require this one, which we call it 4. So for example, like I said, if, for example, there is an analysis course that college is thinking about whether to offer it or no. So if they want to offer, they want to have a very, very strong class. So in that case, number 3 is required. This one will be required if not in that context, but maybe in the context that, well, for example, all instructors in the Columbia College ask college to have at least one good student in their class, so that when they teach, at least one student can understand everything very, very well. So in the context that the instructors in the Columbia College ask the college to make sure that every class in the college is not very weak in the sense that at least one good student is there in every class. Therefore, the instructors can be sure that at least one student can understand the concepts they are teaching. So this can happen in this context, for example. So depending on the context, we may need these types of nested quantifiers. So this one I can say, this statement is true if for every x, p of x and y is true for at least one y. The statement is false if there exists at least one x such that p of x and y is false for every y. So in the context of classes, if we say for every class there must exist at least one student with good GPA, it will be false if there exists at least one class that is very weak, in the sense that no student with GPA bigger than 3.6 is present in that class. So let's look at a mathematical example again. So example, for each x, there exists y such that x plus y equals 0. So please remember the previous case, which was kind of looked at least similar to this, but the concept was different. There exists x for each y, x plus y 0. This was false. Now this time we are interchanging there exists with a universal quantifier. So instead of saying there exists x for each y, we are saying for each x, there exists y. For each x, there exists y such that x plus y is 0. So this one is true. Why is it true? Because, so how can I show it's true? It's true if for every x, p of x and y is true for at least one y. So again, I have to assume that some arbitrary x is given because I have to show that this is true for every x, right? So suppose x belongs to R is given, right? Then x plus y equals 0 is true, right? So see, every x, I have to assume that some arbitrary x is given. Then I have to show p of x and y is true for at least one y. So far I assume some x is given, then I have to show x plus y is true for at least one y. So can you tell me which y value should I consider to have a guarantee that x plus y is equal to 0? Again, remember, I don't know what the value of x is here. It could be 2, could be 5, could be 10, could be -2. But you have to tell me, no matter what x is, what should I choose as y to have a guarantee that x plus y is 0? Y can be taken as minus x, right? Then x plus y is true for y equals minus x. So we showed that for every x, x plus y equals 0 for at least one y. So that means we can say no for every x. So there, for every x, there exists y such that x plus y equals 0, and then this is true. Okay, so this type of nested quantifier will be in particular important in the context of limits. So in calculus or in analysis, when you want to show that the limit of a function is equal to some specific number, we have to use nested quantifier. So if we write as remark, so in Math 225, analysis 1, the nested quantifiers will be used to define limits. So in the concept of limits, you will use it. In the context of continuity, you will use it. And also in the context of uniform continuity, you will also use it. Okay, So let me do one more example. Of the exercises in the book says, so parts of, for example, question 28. Page 71. So for example, let's say part C. We want to show whether this is true or false. So true or false, justify. It says there exists X for each Y, XY equals 0. So this one, if we go up, it was what we called it as 3. There exists X for each Y, P of X and Y. So this statement is true if there exists at least one X must exist for which P of X and Y is true for every Y. So at least one X, if this wants to be true, at least one X must exist such that XY is equal to 0 for every Y. So let's think about it again. So let's think about some values for X. For example, if X is 2, can I say that 2Y is equal to 0 for every Y? Obviously no, 2Y is equal to 0, not for every Y, only for Y equals 0. Or for example, if X is 3, can I say 3Y is equal to 0 for every Y? Again, no, 3Y is equal to 0 for only for Y equals 0. So is there any X that can guarantee XY is 0 for every Y? 2 would not work, 1 would not work, -1 would not work, 0.1 would not work. But what about 0? If I set X to be 0, can I say that 0 times Y is equal to 0 for every Y? 0 times Y is equal to 0 for every Y. Yes, that's true, right? For every Y, 0 times Y, 0 times anything is 0. So this one is true. So you can say set or take X equals 0. We needed at least one X value. Well, I am suggesting that take X equals 0. Then XY will be equal to 0 times Y, which is equal to 0 for every Y. Okay, so this one is true. All right, guys. So we finished this section 1.5. So I will also upload the assignments on Moodle. And as we said before, you don't have to hand in the assignments, but please make sure you do all the questions because in the exams, those questions or similar questions will be used. Okay, so thank you and see you soon.